talking about feedback in simulations.
Hi, everybody. Good morning. I've actually deviated from the title I submitted. I'm actually going to be talking about the abundance of dwarf galaxies, but it's all related back to feedback in some sense. This is work that I've done in collaboration with some very smart people, highlighted down here. And if you have any questions, please feel free to email me or talk to me, obviously. So, like I said, I'm going to be talking about the abundance of dwarf galaxies, and the basis of my talk relates to this plot right here. So we have the stellar to halo mass relationship here, where we have halo mass on the x-axis, stellar mass on the y-axis, and the question that I'm asking is what happens down here? So published abundance matching and other results kind of deviate in what they predict at the very low mass end, kind of probing the ultra-faint region. And so what I would like to ask over the course of this talk is what is the actual abundance and scatter of low mass galaxies, and how do they populate their dark matter halos? So with that, I want to introduce the super dwarf volumes, named after some pretty badass superheroes. They are 4 different volumes: CaptainMarvel, Elektra, Storm, and Rogue. 3 are complete, and Storm will be finished in the next month. They've been run with Chunhua, which I'll discuss in a couple of slides. And they're high resolution, so star particle masses of 400 solar masses, gas particles 1.4 times 10 to the 3, and an effective resolution of 4096 cubed. This talk will focus on results from CaptainMarvel. And if you've heard me give talks before, CaptainMarvel is the rebranding of the 40 Thieves, in case you were wondering. And CaptainMarvel has been run with multiple different subgrid physics. In particular, in this talk, I'm going to be talking about CaptainMarvel in the context of 2 different star formation physics: a high-density threshold star formation recipe and a molecular hydrogen-based star formation recipe. It also has been completed using molecular hydrogen and supermassive black holes with an implementation from Tremmel et al. 2015. I can't emphasize how cool Michael's black hole stuff is and how cool the results coming out of these volumes will be with respect to the black holes. But I can't talk about that today. All right, so I promised you a slide on Chunhua. Chunhua stands for Charm N-Body Gravity Solver. It's a massively parallel SPH code. It's basically the next generation of gasoline. And in particular, I bring this up just to say that it's a new implementation of SPH, meaning it's addressed all the traditional problems with SPH, like the cold-hot gas interface, et cetera. It passes all the tests in Egert's et al. 2011. And so the group has been running with this new and improved code. So here is CaptainMarvel in dark matter density and gas density. We're essentially rotating around the volume and zooming in on my most massive galaxy in the volume, which actually is an SMC-sized galaxy. So my most massive system is SMC-sized. And as we zoom in, we're zooming in on the densest structure, so the densest gas and the densest dark matter. We'll zoom in one more level. And so this is my little SMC, and you can see that there's an abundance of substructure around my little SMC, meaning my dwarfs have satellites around them. All right. So like I mentioned in my introduction, the low mass end of the stellar to halo mass relationship is poorly constrained. So what I have here again is halo mass on the x-axis, stellar mass on the y-axis, and then a few of the different results relating stellar to halo mass. And what I have overplotted on here are the resolved galaxies from the CaptainMarvel volume. Circles are central galaxies, and squares are satellites of these dwarf galaxies. And what I'd like to point out here is that we see significant scatter as we move to these lower masses. So whereas up here the relationship is nice and tight with a scatter of about 0.1 dex, down here we grow our scatter to about 0.9 dex. And then in the colors, what I've shown you is V-band magnitude. So what you can see is that as we go down into this ultra-faint region, if we're looking at something that has a red V-band magnitude somewhere between -3 and -5, so something ultra-faint, there's over a 2 order of magnitude region in which that galaxy can live in terms of its halo mass. So what I'm showing you here is that that one-to-one monotonic assumption behind abundance matching, that the luminosity function maps monotonically to your mass function, actually breaks down at this low mass end. So what can we do as simulators to kind of help people out when they want to populate their dark matter halos and they want to match a galaxy to a dark matter halo? What I'm pointing out on this slide is that it gets even worse if we kind of push the limits of my resolution here. So what we have here is I've included populated halos down to 1 star particle. So you can argue with me about whether that's resolved or not. I know it's not resolved. But what I'm doing is I'm pushing the limit and saying what happens if we go as faint, if I push this as far as I can go. And you can see that that scatter continues to be pretty drastic. And so, like I said earlier, you can't match a single luminosity to a single halo mass, and that spread can be over 2 orders of magnitude once you get down to this faint end. So what's going on here? So the first thing I want to point out is that Tilsawala kind of pushed that definition to the 1-star halos as well in a study he did back in 2015, and he found that the inclusion of baryons causes the stellar to halo mass relationship to bend, and he compared things to the local group data. And what he finds is that there's a bend out here, and what you'll notice is that a lot of the stuff that populates out here in the bend happen to be satellites. And what we find in the 40 Thieves simulation is that accounting for dark matter stripping, because we have a whole lot of satellites out here, reduces the scatter on the low mass end. So what I've done here is instead of plotting log of halo mass at redshift of 0, I've plotted log of halo mass at infall, so maximum halo mass. And what you see is that instead of a 0.9 dex scatter at the low mass end, we've reduced our scatter to about 0.3 dex. So accounting for this dark matter stripping and the infall of your satellite actually reduces your scatter in your stellar to halo mass relationship. So why does the scatter matter? So I want to highlight some great work that Shay did looking at what happens if you add scatter to stellar to halo mass relationships. And it turns out that if you add scatter to your stellar to halo mass relationship, you kind of get rid of the tension between simulations and observations in terms of the satellite mass functions around Milky Way type hosts. And what Shay did in this paper that's really neat is he introduced what he called the growing scatter model, which I'm showing in this equation over here, which essentially is what I see in the CaptainMarvel simulation. And so using his growing, I fit my data to the growing scatter model to derive how the scatter grows as you include in the blue resolved halos, adding more scatter with the 1-star halos, and really pushing the limit, saying what fraction of my halos actually host a galaxy, what happens if I include all my dark halos, and you get different values for how your scatter grows. So now that I have this kind of relationship between what fraction of my halos are occupied and how does the scatter and the stellar to halo mass relationship grow, I can play the game of stochastically populating a whole bunch of halos. So that's what I'm doing here. I'm stochastically populating 200,000 halos. So that's what's shown in the contours with the scatter that I see in the CaptainMarvel volume, and including the fraction of halos that are occupied that I see in this particular run. And so using this abundance of stochastically populated halos, I can derive what happens to the stellar mass function. So what you're seeing here is stellar mass on the x-axis. Number counts of galaxies as a function of stellar mass. In black, we have the no scatter prediction, and in the dashed line, we see what happens to the stellar mass function if you introduce the scatter we measure in CaptainMarvel. And so this gray shaded region is the region currently being probed by HyperSupremeCam, by DES, by MagLight, and what you can see is that we're in the realm of where the observations are coming in, and there's a significant deviation in what you expect if you include scatter and if you don't in your stellar to halo mass relationship. So the point that I'd like to drive home here is that the relationship of the growing scatter and the fraction of luminous versus dark halos is a tool that I've created to essentially help you populate your halos, instead of assuming a monotonic relationship between stellar and halo mass. I don't have too much time left, but I want to give you the caveat that all of this is super, super freaking sensitive to your star formation physics. So like I said, CaptainMarvel was run with molecular hydrogen-based star formation. They predict very similar satellite mass functions, but they predict vastly differing numbers of luminous satellites. So these are just luminous satellites in stellar to halo mass space. The molecular hydrogen one only predicts 4. If you restrict that to ones that are resolved, it only predicts 2 of them. And so this has ramifications on prediction. Oh, well, to explain why, it's essentially because molecular hydrogen based star formation pushes your star formation to much higher densities than a high density threshold. And so you don't have as many halos that turn on before reionization in this particular implementation. And so this changes predictions that you make. So for instance, Coral had a great paper where she predicted the frequency of satellites around dwarf galaxies using the original fire dwarfs. And so I compared what we'd predict in our CaptainMarvel runs, and it turns out 3 different star formation recipes, 3 different predictions, and Coral tells me that the fire dwarfs don't predict any satellites, and well, sort of. She's waving her hand at me. But you can ask her about that. That's not my science. But, I mean, the point is that our predictions are extremely sensitive to kind of the subgrid physics that we include in our simulation. And this is also true in terms of predictions that we're going to make about the stellar mass function. So again, this is expected number of satellites in the H2 run with scatter, the high density threshold run with scatter, and you can see the differences in the faint end of the stellar mass function. And just to kind of tie things into bigger systems, we've also simulated Milky Ways at the dwarf volume resolution and looked at kind of the distribution of satellites and what's going on there. So those particular runs have a molecular hydrogen-based star formation model. And in this model, when we look for ultrafaints in the field, we can't find any. We just don't form them. But we know at least one exists in the field. So what the observations that are happening now and the observations that'll come online with JWST, with more data from DES, Maglite, Hyper Supreme Cam, we'll be able to actually constrain the star formation model in our simulations. And I'd also like to add is, you know, a lot of simulations have a very simplistic model for reionization, and so where and how you implement your reionization actually matters now in the regime that we're probing. So if you have an early versus a late reionization at the faint end, the end that we're currently probing in our observations, you get a vastly different number of predicted galaxies, dwarf galaxies in the field, ultrafaints. And this will have ramification on kind of the quenched field dwarf galaxies that you'd predict. And so here's data, here's simulations, and you know, how this grows and where it goes to fully quenched is sensitive to your star formation model. So with that, I am going to flip to my summary side and conclude by saying that the abundance of dwarf galaxies is largely unconstrained. The traditional assumptions of abundance matching break down. I've tried to provide people a tool with how to populate those particular halos by looking at the scatter in the CaptainMarvel simulation. And I just really want to emphasize that we're now in a regime where we need the observations to constrain our models, and we've got to be incredibly careful about the predictions that we make because we really don't understand star formation in these tiny, tiny, tiny halos. So with that, I'll conclude and take any questions. Thank you. But I mean, but in the regime of ultra faints, they're all satellites right now, and so I don't think it's unfair for me to point out that when someone observes an ultra faint and tries to map it to a halo mass, then you're going to suffer some sort of shift in your halo mass due to stripping. Oh, we can talk about this later, but I have, yeah. So these are brand new runs, and so that's why I said it was extremely preliminary. And so we actually that plot is like made recently, so I'm not sure yet. Like I said, this figure got made like last week, so it's very new, and I would definitely that's the next step to check. Yes. I cannot. Sorry. Yeah, you can. So I measured that scatter and quantified it in the paper, but I didn't know where it came from. But it's quantified in the paper. Yes, absolutely. So that paper is kind of the initial thing. So now that all these volumes are up and running, I have a much larger sample with which to work with. And so the next paper will look much more in detail at what's going on. So this was kind of like the teaser for the original volume. James.
So this is separate from what Mike was saying about scatter and breaking down or whatever, but I mean, it's true that it breaks. So you said that traditional abundance matching breaks down. It breaks down in your simulations.
Sure.
Right.
Sure.
So the question I have is, how do we test that observationally? How do we know observationally that it does break down or it doesn't break down? What would be the way to test it?
So the stellar mass function, right? So that's why I showed the two different stellar mass functions with including different amounts of scatter and different amounts of fractions of halos that are luminous and dark. And you get different predictions on that faint end slope. And as you get to be complete at those masses, the observed stellar mass function is going to constrain what's going on there.
I mean, that's from your simulation, but I mean, one of the subpoints of the paper was shared was that there's a huge degeneracy between scatter and slope in the stellar mass-halo mass relationship. And I would argue that just from counting galaxies in the luminosity function, it's going to be really hard to tell the difference between whether or not it's monotonic, whether the scatter goes up.
I don't disagree with you, but I'm working with what I've got.
But I mean, so it's a more general question, I guess, is how do we test this? I mean, what are the observables that we need to go after in order to say whether or not it blows up or doesn't?
Another great discussion question. Whoever's reading that, you should just add that right onto the slide. Let's thank Ferah again.